Hello everyone, I'm Tiantian He from University College London. Today I'm going to talk about our recent work called Coupled Pathology Appearance and Propagation Models of Neurodegeneration. We have nothing to declare. Let's start with some relevant background information about this research. Our work aims to uncover the underlying complex mechanisms of neurodegenerative disorders, especially Alzheimer's disease. Such kind of diseases demonstrate progressive pathological changes throughout the brain. This work focuses on tau protein, a key biomarker in the Alzheimer's disease, since it has been discovered that the abnormal aggregation of tau tangles play an important role in the process of neurodegeneration. Furthermore, observations suggest that brain connectivity mediates the pattern of neurodegeneration. However, the precise interaction between those two remains uncertain. There are two types of models of how brain connectivity drives the progression of neurodegeneration. The first type of model links the brain connectivity to pathology appearance. The spontaneous appearance of pathology in a region corresponds to some feature of that region's connectivity. For instance, some relate the network matrix called centrality to the mechanism of pathology appearance called vulnerability, by assuming that the nodes with more connections are more vulnerable due to heavier node stress, while some relate another network matrix called segregation to the disease pattern by saying that the more isolated node is more vulnerable since it's more difficult to get nutrition. The second type of model is called network propagation, which uses a differential equation system to simulate the spatial-temporal evolution of pathology. One of the latest models is the two-component network propagation model, which contains two physical processes, the network diffusion along the connectivity, as well as the local replication and aggregation that gives a monotonically increasing trend of the disease trajectory. This propagation model is a good starting point to simulate the disease progression, but it might be a bit simple to reflect the reality. Therefore, we aim to construct a more complex dynamic system by encoding the mechanisms from the pathology appearance to the disease propagation dynamic system by allowing those two to interact in a non-linear way. As a result, we will be able to simulate the progression trajectory underlying coupled mechanisms. We define this two-component network propagation model as our baseline model. And we define our coupled model in the following way. Instead of assuming the diffusion or the aggregation rate is the same across all regions, we weight them with different network matrices that represent the corresponding mechanisms of pathology appearance, as is shown in red. In this way, we combine the mechanisms of appearance and propagation in a non-linear way. Specifically, we put forward 4 submodels to improve the baseline model that doesn't include mechanism coupling. In the first 2 submodels, we consider interaction of mechanisms in the diffusion process, and in the last 2 models, we focus on interactions during the aggregation process. To begin with, let's look at the first 2 submodels, which add spatial distance information to the baseline model that previously only depends on the connectivity density. The first submodel is called distance-guided network diffusion, where we still assume the pathology diffuses along the brain connectivity, but we further weight the rate using the spatial proximity, so the closer the region to the epicenter, the faster the diffusion is. So in the first plot below, you can see that region 1 has higher diffusion rate than region 2, according to our submodel, because it's closer to the epicenter. And the second submodel is called network-guided spatial proximity, which assumes the dominant process is now the diffusion according to proximity rather than along the connectivity, but the rate is adjusted by the density of streamlines. So in the second plot, you can see that generally speaking, the diffusion is more free, but region 3 has higher diffusion rate than region 4, adjusted by the streamline density. The last 2 submodels aim to improve the local aggregation term by weighting the rate of aggregation using two different kinds of segregation, which assumes that the more isolated the region is, the easier for the protein to aggregate locally, since the transportation to other region is harder due to the lack of connections, thus easier to stay. The third model defines the segregation from the angle of the density of streamlines, while the fourth one considers the isolation from the tendency to cluster. So you can see in the two plots below that the darker the color is, the more isolated the region is, the more aggregation of tangles may exist. When it comes to model fitting, our general target is, for each subject, we pick the submodel that describes their pathology pattern best. This includes two steps: to determine the trajectory that corresponds best to the data, and to allocate each subject to the optimized location on their trajectory. The optimization is implemented on the individual level, which means the parameters are optimized per subject, including the diffusion and aggregation rate, as well as the disease onset time. For model evaluation, we use Pearson R correlation between the fitted and measured tau concentration among all 68 cortex regions, since it has been widely used in the previous relevant literature, and it's a simple way to evaluate the similarity between distributions. For dataset we use, the tau SUVR comes from the ADNI dataset, and when we select subjects, we include people who are A-beta positive and at least one region being tau positive. Altogether, we have 205 subjects. And we have two kinds of brain connectivity comes from two separate databases. Now let me display some of our key results to you. The box plots on the left demonstrates the distribution of the Pearson R correlation of all the subjects from the baseline model and the best coupled model, where we can see that the coupled model can capture the disease pattern better for the cohort. The histogram on the right shows the number of subjects best fitted by each model. From this, we demonstrate a potential way to subtype subjects guided by the underlying mechanisms. Finally, let me use three subjects as examples to give you a more direct feeling of the fitting outcomes using the baseline model as well as the best coupled model. Each row represents a fitting for one individual. The scatter plot in the first two columns displays the predicted signal versus the measured signal of each individual. The plot in the third column visualizes the subjects allocated on the optimized location of the fitted trajectory of all the 68 cortex regions using the best coupled model. It can be observed that the coupled model captures the data pattern better. In conclusion, the coupled model captures the measured tau pathology pattern better by considering the nonlinear interaction of disease pathology and propagation. The best fitting coupled model varies among subjects, which may reflect the heterogeneity of Alzheimer's disease, and also demonstrates the potential to subtype subjects guided by the underlying dominant mechanisms. More concretely, geodesic proximity combined with network diffusion most commonly matches the data best. Then, weighting the local replication and aggregation pattern with segregation has also been found helpful, which agrees with the previous clinical finding that the tau accumulation is negatively correlated with cluster coefficients. For future work, the subtyping is currently deterministic, and it's based on our 4 submodels, each coupling the propagation model with only a single appearance mechanism. But we will soon release a more systematic framework, which includes a combination of several potential mechanisms simultaneously, by embedding the topological profile proposed by Garbarino et al. Into our coupled modeling framework in a nonlinear way. And the subtyping process will be implemented in a probabilistic way by assigning each mechanism a possibility. Please keep track. This comes to the end of my presentation. I'd like to thank my organization's founders and co-authors, and I'm very happy to have a further discussion for those who are interested. Thank you so much.